Okay. Hello everyone. So for week three, or rather, today we're going to be discussing the single cycle microarchitecture. So, what is the microarchitecture? Microarchitecture is the connection between logic and computer architecture. So, what is logic? Logic is the familiar stuff that we've seen in our previous classes. It's the stuff that's connected with your gates and how you create them. Basically, the combination of, say, registers and gates are what we have as logic. And architecture is what Mamvion has discussed in the previous week. In the previous weeks, these are the instruction sets, the conventions for how we call subroutines, and conventions for how we use the registers. So, just a simple review of of a powerful logic tool that we're going to be using now is a finite state machine. So finite state machines are tools that we've ended up using to solve complex logic problems. So for example, here we have the finite state machine for computing a factorial. So basically, whenever you start with one, and then you go into the loop state where for every iteration of the loop, you decrement something that starts with the factorial number, and then you multiply that to one. So then you would have something that's going to be n times n minus one dot 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 all the way up to one, and you end up with the definition of the factorial. And then after b becomes 0, because we don't want to multiply 0, after b becomes 0, after b the last b minus 1 at b equals 1, then you go to the done state where the final answer is actually now in um, a. So um, a is now n factorial for that case. So now, what is the single cycle microarchitecture? So the microarchitecture for um, the ARM ISA that we're going to introduce is something that works in one cycle. That's why it's called single cycle. Now, there's this thing called the architectural state of the computer, and that is attached to the 16 32-bit state registers, and also, say for example, the all of the status registers, the XPSR. So the status registers will be also part of the computer state. But basically, you can think of the computer as having a set of states where you go from one state to the other whenever you read an instruction. And then whenever you say have a new instruction, um, like this, you transition to yet another state, and then yet another state, and yet another state. And well, since you have so many state variables, so you have 16 32-bit state registers, and in addition the bits of the XPSR, what you're gonna have is a lot of state. So actually, you're most likely never going back to a specific state unless you say rerun a program, or rerun a program completely, I think. So something to keep in mind. But the main takeaway is you can think of a processor as a finite state machine that whose inputs are the instructions, and because you can change the instructions, it's a reprogrammable finite state machine. So for the processor, we're going to introduce some the state elements first for simplicity. The state elements include the program counter. So you've encountered this before. The program counter is the one that tells which instruction we're reading right now. So the program counter is 32 has stores a 32-bit integer, which is the program count, which is which is the address of the current instruction. The instruction memory is a combinational memory. So what does combinational mean? You have an input. So you start at you have an input, and whenever it changes, the output instantaneously changes. So what happens usually is the PC is connected to this, and it reads an address in the instruction memory, which is then read instantly, not at post edge clock, but it's instantly read through combinational delay and output through this 32-bit bus. We also have the status register. So the 4 bits of status are stored up here. And we have the register file. So the register file is quite interesting. So this is A1, A2, and A3 are addresses of specific registers. So remember that we have 16 registers. That means 2 to the 4, which means we need 4 bits to address. 4 bits to address all of them, which is why we have 4 here. Um, we also have write data 3 here. So actually, write data 3 is the A3 is usually the destination register that we want to write things into, and write data 3 is the data that we want to write into register 3. The register specified in A3, so that's where we put that. There's also a write enable. So when write enable is 1, the next positive edge of the clock, whatever is in write data 3, it was going to be written into the register that's specified by A3. Next, we have the data memory. So for this one, it's also combinationally read. The difference is that here, uh, the okay, the not the difference exactly, but the thing is that when the data memory gets a post edge clock, whatever is in this write data gets written into whatever this address is in the memory, provided that if write enable is 1. So that's write enable as well. So if the write enable is 1, on the next positive edge of the clock, whatever is placed here will be written into this address here. So if write enable is 0, then it won't be written in the next post edge clock. The next thing that the combinational thing about this is whatever address is here, so A will be mem read at A. So it's always going to be reading whatever is seen in A over here. So in order to see how this data path is going to be built, let's try to follow one of the instructions that we've discussed before. So load register. First, we're going to have to fetch the instruction. So we're going to have to connect the program counter to the instruction memory. And then the instruction memory outputs the instruction at the address of the program counter. So that means we have the instruction right here. It's a 32-bit bus. And I placed the structure of a memory type instruction here, since load register is a memory type instruction. So next, we're going to read Rn. So Rn is right here. Rn, we're going to place it into the input A1 of the register file, which makes it so that the data inside register A1 is read combinatorially or combinationally into RD1. And then A2 will also be read combinationally into RD2, but that's for later. The thing to note here is that we're reading Rn from bits 19 to 16 into RA1, which will go out into RT1. So next, we're going to take the extended immediate. We're going to take the extended immediate, um, and then extend it to 32 bits. So basically, this right here is 32 bits because we have an 11-bit immediate here. So assuming that we have immediate addressing for the uh, for the load register that that we have right now. So say here, um, we had an instruction that's LDR R1, say R2, OX04. Then what we have is okay. Let's actually call them RD and RN right now. So this is immediate addressing. So this OX04 will be encoded into this SRC2, which will be sign extended into 32 bits. So this is OX04 in 32-bit form at the output. So what we want to do then is we have the base, right? So the base and the offset. So we're going to want to add the base and the offset. Where is the base? Well, we've already read Rn. Rn has been placed into RA2, and we're going to get it from RT1. So the next thing we do is we're gonna need something to add those, and that's where the ALU comes out, the arithmetic logic unit. So say we have an ALU whose operations are specified here with respect to the control signal. So if you give it a control signal of 0 0, it's going to add the inputs. If it's 0 1, subtract 1 0. It's going to AND the inputs, and 1 1 is going to OR the inputs. So now the thing is, we had Rn here, and then we had the OX04 go in here, and now this is still OX04, just 32 bits now, and this is the contents of Rn. So how do you specify Rn again? Say Rn was a pointer, then this is the contents of Rn. So now we're specifying 0 0, so ALU is going to add them. So now it's what's being pointed to by Rn plus 0 4. I assume it's just hex already, Rn plus 4 or something. And now we pass that into the address and data memory that we want to read, because that's the base plus offset. That's already the thing we want to read. So now the data memory, it reads it combinationally and outputs it through here. So now you have whatever the contents of the thing that you want to read. And now let's call that read data. We want to write that back into the register file. So we put it into write data tree, and then we make sure that A3 is connected to the destination register. So the destination register RD is bits 15 to 12. So we connect the bits 15 to 12 of instruction to A3. And of course, we have to make sure that reg_write is 1 while we're doing this, because if reg_write is 0, or rather reg_write is if reg_write is 0, then write enable 3 is 0, which means nothing will be written to the register file. Since we're loading something from memory to the register file, which that's why it's load register, we want this to be 1. We want write enabled for the register file. Something to note here as well is memwrite. So memwrite is a control signal that we connect to the write enable of the data memory. It should be 0 here. So the reason why it should be 0 here is this write data right here will be someday connected to something else in the circuit, and we don't want that written into the thing that into the address that we're reading. So if we're just reading something from the address, we don't want it overwritten. That's why we place 0 on the memwrite control signal. Okay, so next, the last part, so since we already have the entire path laid out, and we can write the thing into the register that we want to load data into, the next thing that we need to do is now have this program counter read the next address. So we have to make sure that the program counter doesn't just read the same instruction over and over. We want to get PC plus 4. So to do that, we just have to put it through an adder. So it's a 32-bit adder. It's PC plus 4, and then you feed that back into the PC register. So then you get PC plus 4 every time. But we don't want PC plus 4 every time. So what we're gonna do is we're actually going to sometimes take the sometimes take something else for PC. So okay, usually it's PC plus 4, but sometimes we want to use some branch instructions, right? So if we have branch instructions, the source of the PC has to come from somewhere else, usually the ALU result. So actually, this thing is supposed to have a multiplexer right here. So yeah, then you choose whether or not it comes from the ALU result or the read data, the thing that you write back into PC. The other thing is that if you remember, or maybe it's been discussed, or maybe you read it in the ALU manual, or rather the ARM ISA book that was in the supplementary information for week 2. PC plus 8 can always be found in register 15, which is also the program counter register. So we're going to have to write that to register 15 always, and register 15 is always writable from this port. So go ahead and do let's go ahead and do that by adding yet another 4 to PC plus 4, which feeds into register 15, and that should be it for the load register. So, okay, here's what I mentioned earlier. Memwrite has to be 0 for this thing because write data will be connected to something and it's going to have some sort of trash in there. And we don't want trash written into the address when we don't want to write anything into it. Okay, so let's consider a store instruction now instead. So now we have STR, say for example the source register, which is, let's still call that RD, and then we have RN, and then we have an immediate offset OX04. So what happens in this case, this is offset indexing, by the way, since we don't have a exclamation point here, and the brackets include both the offset and the register. So in order to account for store, we're gonna need to see. So first we fetch the instruction, goes into PC, comes out the instruction, and then we pass RN to RA1. We take 1916, and then we pass as well again the base, the immediate offset into the sign extension part. We turn it into 32 bits, so this is now OX04 but 32 bits, and it goes into the ALU. The other one, actually, since we have the destination register right here, we're gonna want to use that in A2 as well. So RD goes into A2 as well and comes out RD2 because we want it to go to the write data. So basically, the write data is actually written inside RD. Why? Well, in contrast with load register, the data that we want to write in store, the store instruction, is actually inside RD. So RD does not take the data. It's not a destination. Rather, it's the source of the data that we're going to write into a specific address in memory. So that's how we use say Rn, and then we put the RD. We put it into write data because that's where the data comes from. Rn, on the other hand, is passed here. So this is the data that's inside Rn, and we add it to OX04. So if you remember, this is called the base. This is called the offset. So what we're doing right here is we have base times offset, and now that goes out into the ALU result. Now, that's the address that we're writing into in data memory. So we place memwrite as 1. So what are the other control signals? We went Rn plus 4. So this is 0, 0 or add for ALU control. Reg write. So we're not writing into anything into RD. RD is still being fed here. We don't want to write anything into RD. We just want to access its information. So we don't want to write anything into the registers. PC source 0 as always, because we want PC plus 4. We're not doing a branch instruction right here. Okay. So next is data processing instructions. So data processing instructions, their structure is written over here as a review. And so for example, we have a data processing instruction with immediate addressing. Say for example, add destination register rn and then ox04. So what happens? First, we fetch the instruction, and then this first one is 19 to 16. That's rn. So the data pointed to by Rn comes out this end, and we're going to add that to an immediate, which is OX04. That's what we want to do in add. So we pass the 11.0 immediate, or rather the immediate pointed to in here. So as you can see, for data processing instructions, the immediate is actually only 8 bits. It goes from 7 to 0, and 11 to 8 is actually rotation. We don't support with this data path. We don't yet support shift instructions, so we're going to throw away rotation for now. And so for the extend block, we tell it to choose data processing immediates for this, which makes it so that it takes the 7 to bit 0 of this one and turns it into a 32-bit immediate. So then that becomes OX04, that's 32 bits, and then RN. So RN plus OX04 comes out the ALU result. So what happens to the ALU result? We go and put that into the mem to reg mux. So now this one is new because now we want to either choose between the data that we read from the memory or the result of the ALU to write into the register file. So we want to write the result of the ALU into the register file now. So we're going to put this one into the ALU result. So we're going to choose ALU result. That's why this control signal is 0, and it goes up into the register file into write data 3, and reg write is 1 because we want to write something. So what's the address that we want to write into? That's RD. RD is coming into here because that's 15 to 12, which is RD. Okay, so anything that we forgot? Okay, ALU control is add, so that's 0, 0. ALU control is add because we were doing an add operation. If we were doing a sub operation, this would be sub. So this would be 0, 1. If we were doing an AND, it would be 1, 0. If we were doing an OR, it would be 1, 1. Next is memwrite. So when we're doing a data processing instruction, we don't want to write anything into the memory, so we make memwrite 0. Okay, PC source. Okay, PC source is PC plus 4. We're not doing a branch instruction. Okay, so that basically concludes it for this data path with data processing instruction and immediate addressing. Okay, next we look at add with register addressing. So add is a data processing instruction. We're going to do RD, RN, and now let's call the next operand RM. So what this basically does is we have RD equals Rn plus Rm. Okay. For this one, first we fetch the instruction, put it here, lay it out. Okay, so what we have from 19 to 16 is actually, this is still Rn. So this is Rn, comes out this end. Okay, so from 3 to 0, what we have here is actually for register addressing, you can see here, Rm is actually 3 to 0. And 15 to 12 is, as always, RD, and that goes into the destination. Now, what we want to do is we add Rn to Rm. So what we actually want to come out of here is Rm. So we choose Rm here. So choose 0, and then Rm comes out of this end. Now, this is also another addition, this multiplexer right here, because it used to be that immediates were directly connected to the ALU. You could not take RD2 to put into the ALU. So now we introduce the control signal ALU source, and we say that the ALU source is actually from the register file. So we choose 0 here, which puts Rm right here. Now the ALU result becomes Rn plus Rm, and then we take that over here and mem to reg. So we choose 0 so that it goes through here, and then it goes up here into write data 3. And now the register that we want to write to is RD. So now that's all fine, and we say okay, write, and so that control signal is 1. So anything we've neglected, im source, so that's don't care. We're not using an immediate. You can see here, because it's not taken, the output of extend block is actually thrown away, so that's a don't care. Allo control. Okay, so we did an add operation, so that's 0 0. Next is memwrite. We don't want to write anything into the memory. You can see here that the address is some sort of garbage, that's Rn plus Rm. It's an address that may or may not make sense. And also write data is also garbage. It's specified by what's inside Rm. So we don't want to write anything. So that's why it's going to be 0. Next, okay, so PC source. PC source also still 0, because we're doing a branch instruction. We're not doing a branch instruction, so we're going to choose PC plus 4 for the next PC. Okay, so that's basically it for register addressing. Add next. Okay, branches. So we introduce for branches, actually the only thing we introduce is actually another mux here for the inputs to the register file. So we either choose the hard immediate 15 or whatever is 19 to 16. So why 15? Okay, let's fetch the instruction first, put the instruction here, and lay it out. So that's this one. So from 19 to 16, okay, we don't have anything in 19 to 16. It doesn't make sense for branch. Okay. Let's take, what do we take? Okay, so branch only has conditions. These things are hard-coded. So L is only 1 or 0, depending on whether or not it's branch and link or normal branch. And we only have an immediate here. So we don't actually read too much from the thing. What we take for branch is actually, we take 15. So reg source, the first bit is 15. The first bit is 1 because we want to take 15. So this is the hard hard register 15. So we want to access register 15. If you remember what's inside register 15, that's actually PC plus 8. So what comes out of here is actually PC plus 8 if we choose 15. And the next thing is that for branch, we take the 23 bits 23 to 0 and pass it into the extend block. And that comes out of the extended immediate block, which is as 32 bits of the branch immediate. And then that goes in. That goes into this multiplexer. So we want to choose 1 here so that it goes through. And so now we have PC plus 8 plus the label. So actually, the thing is, for branch instructions, if you may remember, the im24 is actually equal to the difference between the label. So say it's branch to label. It's label minus PC plus 8. So the difference between where the label is and the next instruction to where the branch is actually placed into M24. So what we're doing here is actually we're adding this M24 with PC plus 8. So if we add PC plus 8, that actually just becomes label. So the address of the label actually comes out here. And now since we have the address of the label, we're going to pass that into here. Mem to reg is 0. And then where we want to get it, we don't want to get it here. That's a nope. So we don't want to write anything into the register file. We put it up here, and actually PC source is 1. So now that we've branched, PC source is 1, and now label goes into PC. Okay, so any controls we've neglected, this is allo control is still add. So it's PC plus it's the im24 plus PC plus 8. So that's 0 0 for that one. Im source is a it's not the don't care. We specify that it's a branch instruction. So that's 1 0. Next, memwrite, we're not writing anything into memory, so memwrite is 0 as well. Reg source, okay, so A2, we throw away this value actually, so it's actually a don't care, the second bit of reg source. We don't care about A2 actually. Okay. So that's basically it for the instructions that that we covered. So a quick review so far with the thing that we've made right here. We can actually do add sub, so you can confirm for yourself how sub would work, and or branch. Branch and link doesn't quite work because we don't have access to the return address yet. um, what else? Oh, LDR and STR. So these instructions are what this data path can do. So data path can do, okay. So data path can do those 7 instructions at the moment. So now let's talk about the control logic now that we have them all. We have the PC source, mem to reg, mem write, allo control, allo source, im source, and reg write. And also reg source. So don't forget reg source. Allo flags goes into flags, which is an input to the control unit. So basically, the goal is to make a control unit combinatorially, combinationally, combinational control unit that calculates according to these inputs and ALU flags. The control signals for the next instruction. So actually, you need to have registers inside control unit as well. So it's not actually purely combinational because you need to store the previous ALU flag, but that's only if you're taking into account the conditionals. So if you're going to implement conditional instructions, you need to take into account ALU flags and you need to store the ALU flags from the last instructions, which is just a register anyway. So you can see that over here. You have registers storing the flags over here. So this is one possible implementation of the control. So they make it here in terms of many different blocks like PC logic, main decoder, ALU decoder, but personally I would build it monolithically after these two ALU flags stuff. I would just write a big truth table of it and then use normal logic design like K-maps in order to actually derive the correct control logic, because it's going to be optimized after that anyway. So yeah, that concludes it for uh, single cycle processors. What So there's two quizzes. You should There's two quizzes on this part as well. So you should try the formative quiz. Um, and Before you do that though, please try to think about what would happen for the sub, or, and instructions. And For also say load register with something like this. You have RN, RM. So the offset is a register offset, not an immediate offset. So what would happen? Do note that this single cycle processor that we've made actually doesn't take into account other indexing uh, protocols, like post index and pre-index. We don't actually support those yet. You can probably you can Okay, try to think of why yourself, maybe. So yeah,